Welcome back to Element 14 Presents. I'm Clem and I've lost my screwdriver 5 years ago and I had to build a robot to retrieve it. This time I dropped my screwdriver again, but I'm not building a robot to retrieve it. I use a broom like a sensible adult. And since I can't reach it directly, I just build a robot to help me get it. We're building robots now. Of course, the only sensible thing to do is to build a network-controlled robot. Out of a robot vacuum, because I had that since 2016. This was actually the first project that I did for Maker Faire Vienna in 2016, and I used it to just carry around a sign. And it was just the vacuum, the broken vacuum robot, an L298N motor driver, and a RC receiver. And I'm gonna review a lot of these parts, but this time we're powering it with a Raspberry Pi 5, dual cameras, and I want to have it real-time controllable from any network device. Quite a challenge. As you know, I like to do things differently. I'm not using ROS, the robot operating system, because frankly I can't wrap my head around how that works. I just rather do it from scratch and just how I want it to be. But I also do something for you, because I just slap on some DIN rails on the robot's chassis, which means you can just attach whatever you want, sensors, controllers, additional dev boards, whatever you need to equip a robot with whatever you want. So this is actually kind of a modular robotic platform. All you need to do is have a broken vacuum robot, some DIN rails and some 3D printable attachments, and you're good to go. In one of my previous projects, I learned how to use dual cameras on Raspberry Pi and stream them over the network. This, of course, comes in quite handy now, because with 2 cameras we can widen the field of view of our robot, which means it's a lot easier to navigate around the environment. And the environment, of course, is my whole workshop. So by having it Wi-Fi attached, I can control it from anywhere in the workshop and by any device. So I can let it run around wherever, and if I case I figured out how to make it autonomous, that also is now on the table. The Pi 5 is quite a power-hungry thing. I mean, it has a lot of computational power, and the motors will also drain quite a lot. And usually you would now have to figure out how to run it from modern batteries. With batteries, there's always a triangle. It's weight, price, and capacity. And usually all the signs point to LiPos, LiFePos, lithium ion, whatever. But this time I actually need more weight to make the spring-loaded motors perfectly engage with the floor. So in case there is not enough weight to my robot, it will slip, it will not work properly. And I also don't want to have too much of expenditure for that one. So the cheapest heavyweight solution that will provide enough peak current for booting up and having the motors run full throttle is just classic lead-acid batteries. 6 volt batteries in that case, usually used for uninterruptible power supplies or for motorcycles. I use 2 of those in series to get 12 volts, and then we use a DC-DC mean well power supply that is directly DIN rail mounted to knock it down to 5 volts for the Raspberry Pi. And of course, this has to provide 5 amps plus, because this is what the Pi 5 can pull under full load. And the motors are directly 12 volts powered. So in total, we're dealing with a power drain of about 5 to 8 amps max. If you have ever tried to power a Raspberry Pi from a battery, you may have run into brownout issues or just powering issues. What we have to do is we have to tweak our power source to the load the Raspberry Pi has to draw. So I basically activate it full throttle, let it do some stuff, and then use a screwdriver to tweak the DC-DC converter to a voltage between 5.0 and 5.1 volts. I don't measure that with a multimeter while tuning it, because I need to know not what the power supply outputs or it thinks it puts out. I need to know what the Raspberry Pi sees on their end. So there is a handy utility in the Raspberry Pi OS that lets you tweak all these voltages from the inside basically. You can see what the Raspberry Pi actually sees. I want to tweak that value, not what I measure on the outside. These could be different. I want the Raspberry Pi to always see a value between 5.0 and 5.1 volts. Of course, I did all the communications via SSH, meaning I'm sitting on another computer and I'm accessing the Raspberry Pi over the network. First, I just tethered it with an Ethernet connection, but once the power system was up, I also wanted to have that untethered, which means Wi-Fi connection, of course. This Wi-Fi connection allows me to run all the software from my remote station. I could just copy files. I can even execute VS Code over there with the remote host function. Spoiler, that doesn't work so great when the Raspberry Pi is under battery power. I don't know why, but it tends to brown out after a few minutes, or it just loses network connection. So I'm just going with straight SSH, and if in case AI has to help me with the code, I just use copy paste and then send over my files or edit them directly over SSH. To connect all the stuff together, of course, we have the DIN rails, but we also need attachments to put stuff on the DIN rails. So what I did myself were these bumpers. So I would have some limit switches on here. These are just micro switches with rollers, and these arms. So in case I bump into stuff, it can alert the Raspberry Pi. Here's a holder for a breadboard, so I can do experimental stuff like attaching some rear lights on here. These are also running out of 12 volts, so they need a level shifter in between. This is the motor driver, same one that was originally used with the chassis, DC-DC converter, and all these little attachments pieces, and especially the holder for the Raspberry Pi. These have been downloaded from printables, and I've linked all the files that I used on the Element 14 community page with sources, so you can download them and use them in your projects. I've been becoming quite a big fan of DIN rails now. I wasn't before, and now I think I will use them quite more often. This is awesome because I can just adjust wherever I put stuff, but it also perfectly holds there. So if I just want to move this out, it's just, it's that easy. The Raspberry Pi is powered via USB. I have made a USB port on some piece of proto board and also attached that to the DIN rail, of course. It mostly holds on there with spite, but it does the job. This allows me to disconnect the Raspberry Pi whenever I just want to power up all the 12 volt systems to test them independently, and I don't have to worry about my Pi not shutting down properly when I make an error. So I can safely disconnect the systems in case I have to. And this also is like a safety feature in case my robot goes rogue. I can just rip out the cable. That is something that I should be easily be able to reach. I don't have a proper safety switch on there yet. The lead-acid cells are from Multicom Pro, and they have a capacity of 3300 milliamp hours. Together they provide 12 volts at that capacity. And in theory, this should be enough to run the Pi and the motors for about 2 to 3 hours, depending on how big of a usage or how intense the motor driving is or the computational tasks. So my goal was to have at least 1 hour of operation at full load, and I think we're doing that quite fine. Welcome to the code void. This time I wanted to have real-time controls. Before it was click, then the framework sends it to the backend, then the backend executes some code, and then the motors start to move. I would like to drive it in real time via just using the keyboard arrows. So this gave me a bit of a trouble. I used Flask, Bottle, Fast API because AI told me to, and none of these will yield any form of real-time controls. It always was just entering a command and then waiting for it to be done. So I want this to be a lot more responsive, and AI to the rescue, it provided me with UV Corn. Haven't worked with that before. That's basically the UV tool set. This is for really responsive web applications, and turns out that's the perfect thing for this. I had to wrap my head around a bit on how this works. The first AI example that I got should only turn on and off an LED. It wasn't that responsive, but I could see, okay, it's already faster than what I did before, and the actual lag in there was in the backend. So by correcting the backend code and using the right GPIO library, because Raspberry Pi 5 works a bit different GPIO-wise than the older versions, you have to be aware of that. And using the LED function in the, I think GPIO 0 is the library that I used in the end, tried a lot of them and none of them worked like I wanted them to. That now turns on the LEDs like I was intending to do. Okay, based on this, then I could write a version of this that would allow me to control the motors. Little problem with that, I didn't wire up the motor driver fully yet. I just wanted to have like a basic control scheme working, so not to waste too much time. And in my first test drive that you can see here, I wasn't able to really navigate because I couldn't run the motors backwards, which means once I got stuck in a corner, I was stuck. What it shows is that the bottleneck in speed is now no longer the connection of me pressing an action and the endpoint reacting. It's now the video stream. This video stream is done at 640 by 480 2 times, which means there's a lot of stuff going on my network. You can significantly speed that up by just reducing the resolution of the video stream, but I left it at this high rate because in this video you wouldn't be able to see much of the environment at lower resolutions, and I want you to have the better experience on the cost of navigating a little bit slower. But why are the colors off? Well, turns out they aren't. This is how the world looks if you can see infrared light. The camera models I used, these are the Pi No-IR, or Noir for black light, but it's No-IR. They have no infrared filter on there. So the shift in color, this is actually the camera being able to see the invisible infrared light, which also means that these will work a lot better at night than I could see with my own eyes. So this robot is already equipped for running around my workshop at night in case I have to check something and I'm not here, but I can control it from afar. So while AI was helpful in getting the right framework, it wasn't helpful in controlling the GPIOs. Funnily enough, it basically tried all the libraries that are available for GPIOs and explained to me how they would for sure work and be very robust, but it turns out it's always used the wrong one. And once we had something doing, I could check that with the pin control function in Raspberry Pi OS to see what it's actually doing. It changed like a pull-up state, or I think it's the change between strong pull-ups and weak pull-ups. And when I told it, you're not controlling the high and low levels that I wanted it to control, you're controlling these pull-up controls, then it told me that's not impossible. It's not possible. You can't actually do that in real time in code. Well, you can. Here it is. And even if I show it the output, it just says that's impossible. So of course I had to tweak that manually. I had a little bit of a fit with the computer and told it all the mathematical terms that are underlying in its model, and then I had to fix it myself. Turns out the LED function in the GPIO 0 library, that's your friend, because that reliably puts a pin high or low. And that also works, of course, for motor drivers, if they work by just pulling a pin high or low. Now that everything's working, mostly, we should just do a test drive. And please enjoy the test drive around my workshop, where I just navigate around and see in what corners I can get myself into and out of again. Oh, I totally forgot about the practical considerations. Of course, the robot can just hand me a broom. Okay, it can try to... Come on, do it. It can try to hand me a broom. It will eventually do it. There it is. Works, kinda. Now we have a fully real-time controllable robot that can run around my workshop, but it's not autonomous yet. So what kind of sensors and processing power should we add to this thing? Any frameworks that you would like to use? Let me know on the Element 14 community. We could attach a ton of sensors in here thanks to the DIN rails, and I'm curious about your ideas. In case you want to build your own, you can download all the files for free on the Element 14 community. I gotta go. There's another project waiting for me.